Well, cool. Whatever. We'll get started without the tablet. So I wanted to talk to you today a little bit like an intro to. No, we'll start later. Like some encryption, some security concepts, like computer science security concepts, not like networking security concepts. So we're going to be talking about encryption, hashing, password security, and we're going to start with encoding actually. So who knows what encoding is?
Well, you want to know like a global concept or?
Yeah, like what do you think encoding is?
Well, basically grabbing some data and um creating creating some kind of hash. I would think that always generates the same thing if you pass in the same data, but it's hard to decode. I guess.
Right. So that's what we're going to talk about because these concepts are kind of fuzzy. They're difficult to differentiate sometimes, right? So what I hope to accomplish today is that we're all going to have a clear definition of what's encoding, what's hashing, and what's encryption. They are completely different. They cannot be used interchangeably. If you use those terms interchangeably, it's kind of like when you're talking to one of those fucking recruiters and they say, "Oh yeah, we use Node and React for the front end." They immediately lost all fucking credibility because they said Node for the front end. So it's one of those things. If you mean hashing, you can't say encryption. That's the most particular one. If you mean hashing, you cannot say encryption because you're gonna sound like a fucking asshole. So let's look at an example of encoding. So let me see right here. So and there's a million different ways to encode something, right? A very popular way to encode data is the base 64 algorithm. So the string "live the thug life" encodes to this in base 64, right? And all I have there is just 3 lines of code. Just 3 lines of code, right? Like str1 "live the thug life," encoded string is new buffer to string base 64 of that string, and then I printed it. So what does encoding mean? There is basically every bit of data, as you guys are aware of, at the end of the day, it comes down to a bunch of zeros and ones in memory, right? So you might have something that string "live the thug life" might encode to a bunch of different stuff like this. And let's just use that for sake of an example. And let me increase the font size, right? And
That's better.
what that does is basically every 6 characters, and this is a particular thing about base 64, right? So not all encoding mechanisms work the same way. If you think about a hex representation of a number is another way to encode data because we have this string, and if we're going to convert it to hex, what do? We break it off into segments of 4, right? And then this one is what? 2, 10, right? So in hex that's 8, and then this one is 11, so in hex that's B, and this one is 12, so in hex that's C. Actually, that's pretty fortunate. And this one is what? What's this one?
No idea, man.
Come on, guys. So like, how do you convert binary to decimal? The first, you're looking at this number. We're converting this number from binary to decimal. This one is 1. So like what we do is we go from the right and multiply this times 2 to the 0. Then this times 2 to the 1. Then this times 2 to the 2. Then this times 2 to the 3. Right? So 2 to the 0 is 1. So let's do this one real quick. In a slower way. So 2 to the 0. So we have 1 times 2 to the 0. Plus, so that's what the binary representation of this thing is going to be. 0 times 2 to the 1 plus 0 times 2 to the 2 plus 1 times 2 to the 1 to the 3, right? So what's this one?
1.
2 to the 0 is 1, so 1 times 1 is 1. What's this one? 0 times anything is 0. What's this one?
0.
And what's this one?
8.
8, right? So the total value of this thingy is 9, right? And so we put a 9 there, right? So the hex encoding, if you will, hex is typically not really considered an encoding. I'm just saying that hex is the same as base 64 encoding. The hex encoding goes from characters 0 through F. So 0, 1 through 3, 4, 5, 6, 7, 8, 9, and then whatever, if this number right here gives you 10, then 10 is A, 11 is B, 12 is C, 13 is D, and so on all the way till 15 is F. So now let's say that we want to encode this in base 64. So we're looking at 6 bits of this at a time instead. So this, and this, and this, right? So we just look at, so let's figure out what this one is first, right? So this is 2, 4, 8, y 2, 10, 16, 32, 42. So this is 42. And this is 64 minus 3, because if it was all ones, it would be 64. And this is, this is 1, this is 1, and this is 2. So 64 minus 3 is 61. And this is 1 plus 4, 5, plus 32, 37. Right? So in order to encode it, all we gotta do is look at this table, right? So 42 is what? 42 is lowercase q. Then 61 is where the fuck are you? 9. 61 is 9. And 37 is, what the fuck is that?
L?
Lowercase l. Yeah, lowercase l. They're in order, luckily. By the way, fun fact, because of this ambiguity, this insane, ridiculous ambiguity where lowercase l looks identical to uppercase I, where the hell are you, uppercase I, right here. Bitcoin doesn't use base 64, it uses base 58 check encoding, which is a less ambiguous type of encoding where anything that looks like something else is not there. So uppercase I, lowercase l are both not there. Uppercase O and 0 are both not there, and there's some other thing that's not there. I don't remember what. So yeah, anyway, this is encoded, right? You take the data and you transform it. You kind of like represent it you represent it in its binary form, but in a more concise way. So it's a way to take binary data and not have to spend one character worth of memory for each, just something that's just going to be a bit. Because if you're translating this over the internet, for example, right, each character is going to be a certain amount of memory that's going to be much larger than a bit. So it's a lot of waste. So that way, when you encode, you actually save some space. So that's all encoding is. Encoding does not protect your information. And it's funny that when you look up something related to base 64 encoding, look at this shit. Is base 64 encoding secure? Fuck no, it is not. All right? So it is a simple translation like this. Obviously, if you have Q9L in base 64, you can reverse engineer that into this, right? It goes without saying. Make sense?
Yeah.
Any questions?
No.
So now let's see. What was it, Frank?
Yeah, it's interesting. I like this stuff.
Cool.
Just
So
go practice it.
yeah, it's a thing that you kind of have to keep reminding yourself of because it's important. Like at the end of the day, there's so many. We're going to talk more about the importance, but there was a story. I think Randy was the one who found it, where he found how essentially there have been like 1,500 MongoDB databases breached or something like that, and it's because people don't know simple things like how to really save a password in a database, such that even if you do get breached, your users are not in danger. How to and people don't know things about networking either. So how to create a virtual private cloud where your servers are not exposed to the internet, and only your web servers can access your database servers and stuff like that. So security is important, and that's what I want to get us interested in this type of stuff. So let's look at the next thing. So this is just base 64 encoding of a single character, and let me start it up again. So the string single A encodes to YQ equal in base 64. B encodes
Can you make that
to
big?
huh?
Make it bigger, please.
Yeah, the thing with this is that so when you have a string, a single character, I think that's
No, I mean the window,
oh
the PowerShell window. Yeah, it's very small.
let me see. My bad. How do I make these properties? Okay. There we go.
Yeah.
So
thank you.
A is encoding to actually two characters, and then that equal. So I don't exactly know where the equal is. I'm assuming that it has something to do with base 64 being designed for it is designed in 6-bit increments, right? And this thing probably takes up something like, let's say 6, 12, 24. Yeah, so this thing probably takes up 24 bits, right? So it's gonna encode it like this, just for the sake of that. Let's try a weird character
What are
here.
you coding?
The same thing, new buffer with the character to string base 64. So JavaScript does it stock. So let's try to put something weird here. What can we put? That's not. Oh, a new line. Shit. Yeah, so it's still, there's probably a character that you can figure out that doesn't end in equal. But at the end of the day, like one character, in regular strings probably takes up, what this means is that it probably, I'm not 100% sure about this, it probably takes up 24 bits in memory. So that's why when you encode it to base 64, it comes out, occupying 24 bits. Make sense?
Yeah.
So now let's talk about hashing. So hashing is a one-way transformation of data. So from hashing, if you have something like this, hello world, and you hash to this, and all you have is this, you cannot actually infer from the hash the original string. So it's very, very computationally consuming to infer from the hash the pre-image of the hash. Okay, so it's basically a one-way transformation. Okay, so and then I'm gonna even write that down. Hashing, one-way transformation. Okay, so this is a lot more secure. If somebody steals this and they don't know which hashing algorithm you used, and it's an uncommon string, then it's very difficult for them to figure out what the original string was. However, if it is a common string, then it's easier to figure out. So we're going to talk a little bit about that later on when we talk about the password security. But there's a bunch of different hashing algorithms, like SHA-256, which produces a 256-bit output. So this right here, let me see. This right here, how many? Where the hell do I have 64 there? Oh yeah, because of the length. So I'm console logging the length as well, right? So the length of this string is 64. So because this is encoded in base 64, each one of these digits represents 64 bits, right? Just like what we were talking about before. So the hashing takes the string hello world and it produces some gigantic binary number, right? But then they're not going to show you a 256 binary number on your screen. So they encode it using base 64. So when you see a hash, typically it is encoded as well, right? But that doesn't mean that they're interchangeable. Does that make sense?
Yeah.
So this hash that we're seeing has a length of 64. And because each character represents 64 bits, this is essentially, how much is 2 to the 64? 2 to the 6, right? Away. Yeah, 2 to the 6 is 64. So 2 to the 6 times 2 to the 6 is 2 to the 12, which is, let me see, 4, 128, 5, 12, 10, 24, 2048. So 2048. So 2048. SHA-256 produces 256 bytes, I guess, not bits. based on the math that we're seeing right now. There's also SHA-128, which produces an output that's half the length of this one. There's also RIPE MD160 and MD5, which is one that is notoriously broken. So this one, somebody figured out a way to actually reverse engineer it. So what I said about if you have a hash, you can't get at the pre-image is not true of MD5, because somebody figured out a way to reverse engineer, to get the pre-image of an MD5 hash. So this should not be used in anything ever, really, unless you're like, for the sake of simplicity, wanting to teach something and simplify things for students. So hashing is a one-way transformation. There's all these different hashing algorithms, and the characteristic of it is that if you have a hash, it is extremely computationally expensive to get back the pre-image of that hash. With a given hashing algorithm, all strings will hash to the same length, right? So the length of the hash of hello world is 64, and if I add a bunch of shit here, which I'm not adding in the right place, password 1 this. So what's password 1, not hello world? Then it's a different hash, right? It's different than what I had here before, like 195 blah blah. It's 15 AC, but it's still 64 bits, right? So what do you guys think? Is it possible for two different things to hash to the same, to have the same hash?
Yep.
It is possible, yeah.
It is possible, right? Essentially, it should be a very easy. Yeah, go ahead, Rennie.
No, yeah, absolutely. I was going to mention, I don't know if you want to mention, it is very, very necessary when you generate these hashes that you use of a random number, so that they really end up being truly unique, which is, your seed, right?
Absolutely, yeah. We're going to talk about the salts in a minute. Go ahead, Frank.
Yeah, they use the date also. They will always be unique. Date with time, with everything.
Yeah, but the date is not a. I'm not 100% sure, but I don't believe is a good practice to use it, because then if somebody is like looking at their victim, they can predict what the salt is going to be. They can predict a range for the salts, and then if they get a hold of the database, then they can screw that victim over. So the date is typically not a. I don't believe it's a good practice. It's considered a good practice to use. What was I going to say?
Yeah, you need something that's going to produce an absolutely random, unique number, and you don't get, even that is iffy, because it's really, really hard to produce something that's absolutely random.
It's impossible to produce. Like, there's no true randomness in computing, right? No. The closest thing is when you use the entropy from the user's mouse or something like that. I don't want to get too much into that, because I could talk a bunch of shit and put my foot in my mouth. It's not my expertise. But I was going to make another point about the random. Oh yeah, so there is a term so there's a specific terminology for this. It's something more than the system time, something more than whatever randomness you derive from the system time. It's called cryptographically secure pseudo-randomness. So that's the academic term for what a salt needs to be. And since we're talking about salts already, let's just go through that all right now and talk about how to protect passwords. So when you have a web application in your database, you're going to have something like this, right? Username, Frank, password, and this is the hash of the password, right? And then username, Randy, password, and this is the hash of that password. If you just hash the passwords and don't salt them, don't include any element of randomness to it, what happens is that, there's this, if it's a big company like LinkedIn, this actually happened to LinkedIn in 2012. They have 40 million users or something. There's got to be, in those 40 million users, there's got to be thousands of people that use stupid passwords like password 1, ABC123, QWERTY1, QWERTY123, right? So what hackers have is this, I guess, instrument called a rainbow table, which essentially is the hashes of all common passwords. So password 1 hashes to this, ABC123 hashes to this, and they have, it's a big table because, this is the base, the SHA-256 hash, this might be the SHA-128 hash, this might be the RIPE MD160 hash. So they have this table where each of the common passwords, they have all of the possible hashes for the commonly used hashing algorithms to each of the common passwords. So if they hack the company and they download the database of the company, they're going to be able to compromise a shitload of people. And the company doesn't salt their passwords. They're going to be able to compromise a shitload of people because they have all these common passwords. They know what they hash to, right? And they're going to be able to hack a bunch of people with that. Does that make sense?
Yeah, but that's what I was telling. I was telling you to. I was what I try to say is not to use the date to generate the whole hash. I used to use the date to be a part of the algorithm of the hash. For example, if you algorithm you add the milliseconds of the specific moment you created the password, that's the thing that makes things a
Right,
lot.
but what I was telling you, Frank, is if I know, I'm attacking you, right, and I download LinkedIn's database, and I know when you created your account, then I just need a longer rainbow table because I can pre-compute the hashes for all of these values. Get password 1 with the date here, whatever the epoch date is here, and then then do it again for 2, and then do it again for
Okay.
3. So I can have a rainbow table anyway if it's the date. If I know the date range within like maybe a couple of minutes of accuracy, then I would only need, it would only multiply the work of computing the rainbow table by about, if it's a couple of minutes, it would be, what is it?
No, I get it.
I can't even, 1,000 per millisecond, 60 per minute, so 60,000, 120,000. It's a linear factor, it's not that much. So let's see. So let's see how passwords are actually protected. Typically, you don't want to reinvent the wheel, right? You want to use a library. Like right now, everybody uses bcrypt, but Argon 2 is a library that actually a hashing function that actually won some kind of hashing competition. Argon and bcrypt both salt first, and then they hash. Like we've been discussing. Except the salt is more random than just the system time or anything derived by the system time. The requisite of the salt is that it has to be a cryptographically secure pseudo-random.
What's the difference between Argon and bcrypt? Do you know?
No, I don't know. I don't know the math behind it. I just know that Argon is supposed to be kind of like the new kid on the block. That's even better.
I'm gonna check that out.
See, so let's Argon 2 actually. So let's look at the output of all this stuff. So the string Argon 2 password hash 2. I'm just repeating the same thing 3 times, right?
Right.
Basically, and this is just the line of code that you get from their npm page, which documents how to hash. So if this is my password, these are the options, the expensiveness of the. So you can configure hashing functions like bcrypt and Argon 2 to have like, to lower the cost or raise the cost of time and memory and use parallel processing and stuff like that. Because basically what you want to do is, depending on what your budget is, how much money you can spend on servers, you want to use the most expensive. You want your hashing function to be as expensive as possible because that'll be more secure for your users. So I'm basically just taking the same password, hashing it 3 times with Argon 2, and look at what it stores. It says $argon2d, v19, m8192, t4, p2. Then some amount of this, I don't even know how much, some amount of like the first few characters of this is the actual salt, and the rest of the hash is the hash. Does that make sense? So they store some information about the salting that was done, then the salt, and then the hash. That's what Argon 2 stores. At the very least, you will always see the salt concatenated to the hash. So the first whatever binary digits will be the salt, and then the rest will be the hash. Or vice versa. It could be at the end. It could even be in a separate column of the database. It doesn't really. But typically, you store it's 1 salt per user, and you store it in the database with them. And there's got to be some kind of way that the algorithm can figure out on its own which one's the salt and which one's the hash. So from this, Argon 2 is going to be able to figure out which salt it used to encode this password. And then when the user tries to log in, they log in with username Frank and password whatever. Based on this, it adds that salt to the password whatever, hashes it again according to all these parameters with V and M and T and whatever, all being the same. And then it sees if it got the same result. And if it did, then the password is valid. If it didn't, then the password is invalid. Make sense?
Mm-hmm.
Okay.
Cool. Yeah, so this is what
there's an exercise on Code Wars that it's actually a kata, I think it's SQ1, that is to basically something like you have to figure out what the hash is doing.
Cool.
Really interesting. Let me find that. I'll send it to you.
Cool. So now let's talk about encryption. So encryption is a totally different thing from hashing. What would you guys think is the difference? Now that we know what hashing is, what would you guys think is the difference between encryption and hashing?
Hashing is one way, and encryption is also one way, right?
No.
No?
That is the key. Hashing is one way, encryption is two way. So anything that you encrypt, you want to be able to decrypt it. It just requires a key, right? So let's see an example. So let's see an example of encrypting something. So we're gonna get this file, sample.txt. This is a text file, right? And it already ran it because I'm running NodeMon. And then I'm getting sample.txt, and I'm gonna encrypt it as sample encrypted with the AES-256 algorithm, and this is my secret key for encryption. So this is the difference right here, right? So encryption is basically a transformation of data that requires a key. Okay, so given the key and the algorithm, you can decrypt it, but without the key, it's extremely computationally expensive to decrypt the information. So let me see this. What happened here? All right, so here we go. Here's my sample encrypted, and it's just a bunch of shit that the character encoding doesn't even support. That's why I have so many question marks and stuff, right? But it is encrypted information. And how do I know that it is correctly encrypted? Because I'm going to decrypt it right now. I'm going to jscrypto.decrypt file. I'm going to decrypt this file and save it as this one. So I'm going to delete this. Save it as this, given the same thing with the same password. And I forget what this actually is. And then the callback, right? In the callback, I'm just gonna console log when I'm done. So let me go ahead, comment this.
I put the link on the Slack.
Awesome. And then when I go to decrypted, this is a text file. So I went from here, this is a text file, to this, right? And given the correct password, I was able to get back to this. Right, so that's what encryption is. It's essentially a two-way process of protected data that requires a key. So that is at least one key. So that is the key concept, is to understand that encryption is different from hashing in that it is a two-way thing and it requires a key. Make sense?
Yes.
Oh, guys, but by the way, I just want to mention, you guys probably heard by Google from now on is going to start marking any pages that are HTTP as insecure. So they're really pushing for
I thought that was actually going to happen like in October or something, and I was kind of like bracing my beehole for it, and then it didn't happen. I was racing against time to update FBI.edu and techlaunch.io and apps.techlaunch.io and all these domains, and then it didn't happen. So
well, it's going. They just announced it, I think like 2-3 weeks ago. That's going to happen, and they put a date for it. I don't remember what it is, but they're just letting everybody know. To give everybody time to move to HTTPS, but moving forward, I don't remember what D-Day is for that. But if you're running an HTTP site, you're definitely going to get penalized. So I think we need to get our students to start working with HTTPS because not all of them have no idea.
Yeah, that's true.
Yeah.
Yeah. So, speaking of HTTPS, what does HTTPS do?
So HTTPS encrypts your data on one end, and it gets encrypted on the other using SSL.
Mm-hmm. Definitely. So the
basically
data coming. Yeah, go ahead.
So that in transport, you're not sending clear text over the wire, basically.
And why is that super important?
Because you can have man-in-the-middle attacks where somebody stands in the middle between the two sides and basically take the information, and bam, that's it. You're compromised.
Do you need so much sophistication as a man-in-the-middle attack to be able to profit from somebody doing some important operations without HTTPS?
Not really, man. You can you can even sit there at a cafe with a sniffer, and you can just pick out the stuff flying over the.
Exactly. So that's the key thing that most people don't understand, right? Like if you are connected to the same router device to the same gateway as somebody else is connected, you can see all their packets, right? So if the packets are not encrypted, you can see everything they're doing. You can see everything they're sending. So if they log into a website, while you're on the same network and you have packet sniffing software running, you will literally be able to see all the unencrypted packets, and it's just a matter of assembling them back together and seeing what the payload of that post request was with the username and password, and then boom, you can hack them.
Yep.
So it is very, very important to have HTTPS, and to, if there's a website that doesn't have HTTPS, never ever type anything into it. Make sense?
Especially credit cards and passwords.
Exactly. Yeah, credit cards, passwords, even like your social security number, whatever. Like there's so much shit. Like, yo, the name of your pet, they can use that shit to hack you. You know, because if it's your security question or whatever, you know.
Yeah, it's really interesting to sit at a Starbucks with a sniffer.
Yeah. So let's talk a little bit about how anybody know, like, have an idea of how the encryption tunnel gets established between the client and the server for HTTPS?
I don't know. I don't remember the details right now. But
So there's basically, let me see if I write out the steps here. Client goes, yo, I wanna connect with you to the server. I don't remember if specifically the client says first, this is what I support, or the server is the one that responds with, okay, cool, this is what I support, right? Yeah, no, actually, it's probably here. This is what I support in terms of encryption, right? Encryption algorithms and stuff. Okay, cool. This is my public key. So let me not write what I'm not sure of. I'm sure of that the client goes, yo, I want to connect with you to the server, right? They actually do a handshake for TCP IP socket, right? So after step one, we already have a connection established between client and server. Server goes, okay, cool, this is my public key, and then sends it to client. Client decides on what symmetric encryption algo it will use, and generates a random key for it, then encrypts this info and sends to server, and it encrypts it using server public key. Okay, so so far what have we done? Client goes, yo, I want to connect with you. Server goes, okay, cool, this is my public key. The public key is something that the server has available for anybody. So anybody who wants to encrypt something and send it to the server, the only entity that has the private key, which is capable of decrypting that information that was encrypted with the server's public key, is the server. So hopefully, right? So the client decides on what symmetric encryption algorithm it'll use and generates a random key for it, and then it encrypts all this information and sends it to the server. So it's basically a little file, if you will. Look, this is the algorithm that I'm going to use. This is the key for it, and this is how I'm going to send you all the data, right? Then server creates a session for client and remembers key and algo. So from then on, anytime that the server is going to send something to the client, obviously the server cannot send something to the client and encrypt it with its own public key, because the client doesn't have the private key, right? So it wouldn't be able to decrypt it. So that's why we need this handshake process, so that they can agree on a way to communicate. So now when the server goes to send something to this particular client, it goes into the session object and figures out what the key and what the encryption algorithm is, encrypts it with that, sends it to the client, and because the client knows which random number it generated to encrypt, then it's going to know the key to decrypt. But the key thing here is that the actual encryption is single key encryption. It is not two key encryption, which, there's those two kinds of encryption. So that's another thing that we have to differentiate between, which is the fact that it's possible to have single key encryption, which is what we saw here, or two key encryption, which is, you have two different keys. One of them encrypts and one of them decrypts. And, they call them public and private keys. I wish they would just say encryption and decryption key, because which one is public depends on the application. So in HTTPS, the public key is the one that's used to encrypt, and the private key is the one that's used to decrypt. But in Bitcoin, the public key is the one that's used to decrypt, and the private key is the one that's used to encrypt. So the important thing to remember here is that thinking that the public key always encrypts is a mistake. That is not the case. There is a public key and a private key. Which one encrypts and which one decrypts is based on the application. That make sense?
Yeah.
All right, so let's run through that process one more time. What do you guys remember? So what are the 4 steps of HTTPS, establishing an HTTPS connection?
Yeah, so basically, beginning, one of the servers says, "Hey, yo, and I'm going to connect. Here's what I'm running." Then the server responds, "Okay, so that's fine. This is what I'm running." They shake hands, basically establish a connection.
Yeah.
The server response sends the public key.
Yep.
And now what?
So there's not.
What?
There's like a couple more steps left. So client says, "Hey, I want to connect." Server responds, "Okay, cool. Here's my public key." And now what?
Yep.
Now they have to agree on a hashing on a encrypting a method, I guess.
Yeah, on an encryption algorithm. And what happens now? The client generates a key. So just like remember, encryption always requires a key. So this was our key when we were encrypting stuff before. So the client generates a random key that only it knows about, because it generated randomly at that point in time, and encrypts it with the public key from the server. Now that it's encrypted, nobody in the world can decrypt it, because in public key infrastructure encryption, whatever the public key encrypts, only the private key can decrypt. Well, whatever the encryption key encrypts, only the decryption key can decrypt, right? So
is it possible that it changes over time?
Yes, every time you connect to the same server, you're going to generate a different encryption key. And every time you connect to every different server, you're going to generate. That's why at that moment in time, you're going to generate a random number, and that's going to be your encryption key. So you're going to, because you can't send it over the wire, because if somebody just happens to be watching while you connect to the server, then they can know your encryption key and they can impersonate you. So you have to encrypt it first, which is why the server had to send you the public key first. So with the server's public key, you encrypt your own encryption key that you randomly generated a split second ago, send it to the server, and now the server has it, and it's like, okay, cool. Now everything you send me, I'm going to decrypt it with this.
There's one additional wrinkle in all this, which is what certificate authorities were supposed to deal with.
Right. Well, so when the server sends the public key, what it sends is actually the certificate. So the public key is one of the elements of the certificates. But if you want to talk about certificate authorities, why don't you tell us what are certificate authorities and what are certificates?
So the whole idea. Okay, Frank, you want to take that one?
No, go.
No, so the whole idea behind a certificate authority is sort of saying, okay, so we have two people that want to communicate with each other, and the thing is, how can they trust that they are who they say they are? Because obviously we're not face to face, right? So there's an issue of trust. So the solution that was found was, okay, well, we're going to have a third party designate that, yeah, I know both of these people, and since I know them, I can guarantee to both of you that, person A is who they say they are to person B, and vice versa. So what the certificate authority does is they sign the certificate that is then put on the server, which when you connect, and if you connect to that server, it's guaranteed because it's checked with the certificate authority, right?
Yep.
It's guaranteed.
That's what you.
Yeah. So basically, that person that you're connecting to is who they say they are. It's like they present their ID to you and saying, "Hey, this is my ID. This is who I am," and that's the idea. That doesn't really, I don't think it really fully works. Honestly.
You have to register. You have to register with them or something like that, also.
I'm sorry?
Yeah, you do. You have to register with the certificate authority.
There is also a way to create like a local.
There is a way to create your own self-signed certificates with OpenSSH, I believe, or OpenSSL, and you can, but that is not going to be accepted by the browser. So what happens is every server that wants to use HTTPS needs to have an SSL certificate. Part of what the SSL certificate has is the public key, right? And it has a bunch of other shit. that I don't understand 100%, but some of what it has, another thing that it has is a signature. So the signature is, there's some kind of cryptographic way of verifying that signature was actually issued by a certificate authority. And your computer, let me see. Your computer actually has knowledge of certificate authorities. So let me show you right here. What's that? Net. Let me go back here. Shit. Where's the network stuff? Network and sharing center. Fuck. Where's the internet options? The old Windows 7 internet options.
Oh, right there.
Details.
Isn't that at the bottom? Like on the left?
Properties. Yeah, here we go. Right here. Where's my TCP IP thing? IPv4. Properties. No. Where's that?
You gotta go up.
There's a place, I forget where it is. I'm not going to spend any more time trying to get to it right now. But there's a place where you can literally see all the certificate authorities that your computer knows about. Okay, so your computer knows about the certificate authorities, and it has some kind of way to validate whether a signature by a specific certificate authority is legit. So when the server goes, okay, cool, this is my public key, this is my SSL cert, let's amend that, right? Public key, signature, etc., right? Your computer already knows about some kind of way to verify the signature, if the signature is legit, given the certificate authority that this SSL certificate claims to be issued by. And that, helps the computer basically determine, oh yeah, this really is google.com. Make sense? So yeah, the SSL certificates are very important as well. And this is the step where they get sent back to the client. After the client essentially requests a connection, the SSL cert contains all the information that's necessary for the client to do the third step in the handshake. That makes sense?
Yeah.
All right, cool. Let's look at the code that we have.